today's video will focus on the fundamentals. How can we find a derivative from absolutely first principles? In order to do that, let's imagine that we have a function f of x against x, as we have plotted on this graph over here. And for the purposes of this video, we're going to assume that this function is fully differentiable, very smooth, and within the regions that we're going to be differentiating. If we wanted to find the derivative at a certain point, let's say we pick a point over here. Let's say that this point, let's just give it a name. So let's just say that this is a. Now the derivative will be the rate of change of that function. In order to find the rate of change, what we'll need to do is draw the tangent line on this function at this particular point. I think technically this line is actually called the secant line, and let's just imagine that we have a tiny interval a, and then let's say that over here we have another point which is a plus h. So the distance between a and a plus h, which is just this distance over here, is of course just h. So that we're going to have a line which essentially is connecting those two points. Now what we're really interested in is actually the slope of this line, which is connecting a and a plus h. Now the derivative is defined as the gradient of this line. So let's just say that the derivative, the rate of change of that function, will be equal to the gradient of this line over here. Well, remember, the gradient is simply change in y over change in x, which would of course be equal to change in y, so that's y of the second point, which is this point over here. So that's going to be f of a plus h, and then we're going to be taking away our initial y point, because delta y, of course, let me just write that here, is y2 minus y1, and delta x is equal to x2 minus x1. So this would mean that this is equal to f of a plus h. This is our y2. Take away y1, which is just equal to f of a, like so. Then we're going to be dividing that by our x coordinates, or the difference between the x coordinates. So our x2 is here, which is a plus h. Then we're going to be taking away a. Let's just simplify this a little bit, and this will be equal to f of a plus h, take away f of a. We're going to see that the a's are going to cancel, and what we're left with is just the h. And now this is where the truly genius idea of differentiation of calculus really lies. Imagine that this interval over here becomes infinitely small. We're going to start to think about these limits, and the derivative will be defined. So let's just call the derivative f prime of a. So the derivative of this function at point A is defined as the rate of change, the gradient of the tangent, when this h starts tending towards 0. So we're going to need to define this as the limit of this function as h is approaching 0. Now let's see whether we can apply what we have derived so far to an example. We have a little function here which is y is equal to x squared, and we want to find the derivative of x squared at x is equal to 5 using first principles. Now just for demonstration purposes, I'm going to show you what we'll normally do in this situation, which is to find the derivative of x squared. So let's just differentiate this very simple function. So d by dx of x squared is of course equal to 2x, and of course at x is equal to 5, this means that d by dx, the derivative of x squared is equal to 2x, which is equal to 2 times 5, which is equal to 10. Now, how do we know, though, that this is actually true? How do we know that this rule actually works? Well, let's see whether we can do exactly the same using the definition of the derivative which we looked at previously up here. The derivative of x squared at that point will be, let's just call that f of 5, or f primed of 5 will be equal to the limit as h approaches 0 of f of a plus h. That's going to be f of 5 plus h minus f of 5, like so. And then we're going to be dividing that by h, which will start tending towards 0. Okay, well, this is equal to the limit as h approaches 0 of, now f is, the function is x squared. I'll just write this down over here, that y is equal to f of x is equal to x squared. Now, x squared, when x is equal to 5 plus h, will be equal to 5 plus h squared minus 5 squared, like so. And then we're going to be dividing that by h, which is equal to the limit of this function as h tends towards 0 of 25 plus 10h, because it's 2 times 5 times h, like so, plus h squared minus 5 squared, which is 25, and then we're going to be dividing this by h. We're almost there, guys. Let's just do a little bit of algebra. So we can see a 25 and negative 25 are going to cancel out, so this is equal to the limit as h tends to 0 of 10h plus h squared. Let's just take a factor of h out, so it's going to be equal to h, open brackets, 10 plus h divided by h, and this cancels out, and what we're left with is the limit of this function as h tends to 0 of 10 plus h. But notice that this limit is just 10, because as h approaches 0, well, then this whole function approaches 10. And the two results agree perfectly. Okay, guys, so hopefully you found this video very useful or interesting. If you've ever wondered why the rules of differentiation are just like that, virtually all of the rules of differentiation are derived from first principles. We looked at the fact that the derivative of a function is equal to the gradient of the secant line, and we used the rules for essentially calculating gradients and a little bit of calculus with the limits to derive this formula for differentiation from first principles. Thank you very much for watching, and I'll see you in the next video.